Data management, best management practices. The primary objective for collecting data is to provide information about how the resource has responded to management. The primary outcome from collecting data is that we're able to make management decisions that are informed by data. Information provided by data gathering activities needs to be both accurate and credible. As we see in this diagram of the adaptive management cycle, the data gathering or monitoring the resource is the primary step before we can determine whether or not the objective has been achieved. Let's review this in a little closer detail. We state our management objective, which clearly states the desired condition for the attribute of interest. And we then follow that with a sampling objective that clearly states the desired precision and confidence that we want in our estimate. We develop a monitoring plan, and in doing this, design how the sampling is going to be conducted. The next steps are to collect data, analyze and interpret those data, and then use the results to inform management. In this presentation, we're focusing on the actions involved in monitoring, so collecting, analyzing, and interpreting the data so that we can inform management and determine whether or not the objective has been achieved. Now, data management involves many stages and many steps in the entire process where we're working with data. So starting with data collection, moving to data entry or transferring that data into electronic formats. Then in the data analysis step, we often manipulate or convert our data and then summarize it. And then we take our results and interpret them and report those results. It's always important to do a reality check. Because collecting and working with data has so many steps, there are many places where we can introduce non-sampling error. Essentially, this represents a chain of events, and there's a potential for weak links. Now, we've all heard the term garbage in and garbage out. We work hard to collect our data, and we report our findings from our data gathering activities so that people can make decisions about management. We put our names on those reports, and we really want to avoid producing anything that someone may consider to be garbage. So what we're going to be doing now is looking at a few best management practices, a few ideas about things that you can do to help avoid creating non-sampling errors and we want to make sure that we produce data that are credible. Now, there are two major activities involved in data collection: collecting the measurements and the observations and recording them. First, when we are preparing to do this, we want to clarify that all of the ground rules and all of the methodology for the people who are going to be taking measurements and observations. We want to make sure that we carefully train and calibrate our observers. Now, recording data actually involves training as well. We want to make sure that the data are gathered using well-designed data sheets and that the recorders are clearly trained on how to record that data. Usually we want to practice both of these activities simultaneously and then review them in the field. This enables us to identify any problems that may exist and address them so that they do not create problems down the line. There are certain problems that are associated with data collection, and what I'm going to focus on now are the problems that are associated with recording data. First, inconsistent data recording, how to deal with missing data, and then poor handwriting are all problems that occur with data recording. Let's examine each of these and what best management practices we can use to avoid them. For inconsistent data recording, we want to clarify the terms and the formats as they should be entered onto the data sheet. For example, we establish species codes that we use. We have to decide how to name our species, and we want to use just one set of terms. For example, we could use, if we're measuring, if we want to write down black grama, we could abbreviate that either BLGR for black grama or BOER for Bouteloua areophyta. In general, we focus on using the species names, and so we would select BOER in this case. We also need to establish the terms and the abbreviations to be used so that we can be consistent. We want to use only one term and only one abbreviation. For example, when we're collecting ground cover data, some people call it soil and other people call it bare ground. We would want to establish that we could use an S for soil or a BG for bare ground, but we'd have to determine which term we're going to use and make sure that all observers consistently use only one term. Now, how do we deal with missing data? First, we want to set some protocol for how to complete forms. Remember the importance of metadata, so we want to make sure that we have metadata on every sheet. This means that each sheet has information telling us what the site was, what the sampling unit ID is, the date that the data was collected, and the observers' names, as well as other information that needs to be tied to the actual data that's on that sheet. If you don't have metadata that tie the data on the sheet to the location, it's basically worthless. We also have to have a procedure for indicating repeated data, because recorders will get tired of writing the same words over and over again. We see two examples here. On the left, there are some large areas that are left blank. Now, we don't know if that means that data wasn't collected or if it was. And so if we have a protocol that we use, as the observer, the recorder on the right used, just by putting a slash or a line to indicate that that this is repeated information, and so for example, B here for the soil surface should be assumed to follow until it's changed into a different indicator. Poor handwriting can be addressed by making sure that the recorders know that they are writing to communicate. Handwriting must be legible because sloppy letters and numbers often result in data entry errors. We can see in this example some fairly sloppy numbers, and this is gap information taken on continuous lines, and so then the gap size is calculated based on these numbers. We see in the example on the right the same numbers written more neatly, and if we compare them, we can see that there are some differences in the gap size that is calculated. For example, instead of 1500, this was interpreted as 1800, and so it resulted in a difference between 310 and 10. Because of this, the total gap for that was true is the accurate gap, 718, is misrepresented by the information on the left. We see a difference of 250 centimeters in a 25-meter line. And remember that these errors are undetectable because they are non-sampling errors, and they affect the accuracy of our data. Now, let's look at additional data collection best management practices. We want to check the quality of the data as it's being collected so that we can make corrections in the field. We want to take photo points in order to document the conditions. Sometimes this can help with a reality check if we need to do one later on. We also want to do all we can to avoid worker fatigue, boredom, and physical stress. Oftentimes to do this, we would trade jobs periodically, make sure that our crews take breaks, and that they're prepared to be working in the elements so that they can work safely. Now the next step is data entry, and there are problems associated with this because it's time consuming. We need to have a protocol for missing data, and also we need to know how to deal with typographical errors because they will occur. Let's look at each of these in detail. First, we streamline for efficiency. We do this by carefully designing our electronic data sheet. This facilitates data transfer. We will make fewer mistakes and fewer omissions. It's important to be sure to include fields in the electronic data sheet for metadata and also for any extra notes, information about species code, and other information that needs to be retained with the data. Essentially, we want to make sure that all of the information that's on the data sheet stays with the data in its electronic format. Now, missing data happens. We need to set a protocol for dealing with missing values. Missing data occurs because there can be recording errors in the field where someone may forget to write something down, or we may miscalculate the number of sampling units that have been measured. We have to know how to indicate electronically that the data are missing. And it's important that we don't insert zeros for missing data. We'll look at an example about that in just a minute. Also, typographical errors, they happen. So what we do is we cross-check our data to verify its accuracy. First, we compare the paper copy to the electronic copy. Do this line by line and cell by cell. It's important to do this because typographical errors happen, and the only way you're going to catch them, the first step in catching them, is to compare the original to the electronic copy. Next, we want to examine the data electronically, and we can do this by either sorting or filtering. We look for abnormalities in the data, extreme values or outliers, and unusual formats. So let's take a look at a spreadsheet and to see some of these examples. Here we see a data set that was collected, and there are 20 observations that are made on 3 different species. There is one missing transect here, and what we're going to do is look at what happens to your output if you insert zeros in place of the missing data. We've already done the data analysis, and so I'm going to pull it over here now. And you can see that by comparing BOR1 to BOR2 and ARPU1 to ARPU2, that the mean values change, as does the standard error. So our estimates of precision change as well. So the standard error and the standard deviation change. And what we have done by including zeros is we have artificially established that in line 15 the value of BOR was 0. We don't know that that's true. We could have entered 50 and we still wouldn't know that that was true. So we don't want to use a 0 because zeros mean something. They mean that nothing was there. Let's look at another example of sorting data. In this case, we've already entered the data, we've already checked it, but we want to use a couple techniques to see whether the data have any abnormalities in them. And so these are cover data that have units of percent, and what we can do is we can take these data, and they've already been totaled. We know that percent data cover data in percent has to be bounded by 0 to 100. We would not have any values that are over 100. And so, so what we would do in this case, oh gosh, here, let me try this again. Okay, so what we would do in this case is sort the data by the total, and we're going to put the largest on top so that they will pop out at us. And we can see that there are 3 transects that have data values or total values over 100%. These are suspicious, and we can see a couple numbers that seem likely to be wrong. So before, we can't change these until we know what the actual values are, so we would have to look at the original data sheet. Let's look at one other example, and this is showing how you can use filtering. In this case, what we would do is highlight these cells here and turn on the filter feature. And then what we can do is we can look at different columns and we can see what the values are. We see that 100 is very different from the other values, and so that would raise a red flag that maybe we would go look at this 100. Maybe we would go look at this 116, etc. Okay, so that's how we can deal with typographical errors. Now, when we're doing data analysis, we also have to consider best management practices for mathematical conversions as well as reorganizing our data. When we're reorganizing data, we want to make sure that we rearrange very carefully. When we're doing mathematical conversions, we want to make sure that we use correct formulas. So again, we're going to very quickly look at the Excel data sheet. In this case, we're going to look at formulas, and these are density data that were collected in transects, in belt transects. The belt transects are 15 meters squared, and in this case, 1 meter by 15 meters. So before we start plugging and chugging, we want to make sure that we have a formula that works, and we want to verify that formula by testing it. So I'm going to set up a formula here that I would use to convert the number of plants per transect to the number of plants per meter squared. I'm going to set up my formula as though it was sitting here next to the actual data. So what I'm going to do is tag the data cell, and then I'm going to divide that by 15 because my transect was 15 meters squared. And I'm going to have to convert these data to the number of plants per hectare. And so in order to do that, I would set up another formula where again I tag the cell where I'm going to be using that data, and then multiply that by 10,000 because I know that there are 10,000 meters squared per hectare. Okay, and now I've got my formula set up, but I'm going to put in a number where I know what the answer is going to be. If I have 15 individuals in a belt transect that is 15 meters squared, that should translate to 1 plant per meter squared. And sure enough, it does. I feel good about my formula now. I also know that if I have 1 plant per meter squared, I should have 10,000 plants per hectare. So now I can copy these formulas over here, copy them again down here, and now I've converted all of my measurements into units of the number of plants per meter squared and the number of plants per hectare. So now let's look at interpretation, best management practices. Before we start to actually interpret the results, we want to do a couple of reality checks. We want to look for red flags in our data, and we want to make sure that the data makes sense. So how do we look for red flags in our data? Again, if we look at the Excel spreadsheet, and this time we're going to look at a data set that had 20 transects, and so there were 20 sampling units. We've already analyzed the data, and I'm going to pull that in over here, and it's summarized over here, so we can see that we have mean values, standard deviations for each one of the species. But before I get too far, I want to make sure I'm expecting that my sample number should be 20. And when I look at the count, I can see that it's not. It's only 15. So when I did this analysis, I must have only pulled in maybe the first 15 rows of data instead of all 20. This kind of simple reality check is very important to make sure that you don't interpret results that are flawed. And then reality check number 2. Does the output make sense? Okay, we just did that. Does the output make sense? We should always have a ballpark figure in mind for what the values of what our results should look like. Obviously, we don't know what the exact results are going to be, but we have a pretty good idea. So we should have a ballpark idea or figure in mind. Let's think of going back to that photograph that you took when you collected your data. If this is what your site looked like, and you're measuring bare ground, and you're measuring ground cover as well as canopy cover, and your results produce something that suggests either this scenario or something as extreme as this, you may want to do your reality check. Neither one of these in the middle or on the right resemble what you would have imagined for your reality check and for your ballpark figure. And so based on doing this reality check, I would go back into the data and review it very carefully and see why the information that I'm getting is telling me something that seems very abnormal. It could be that this really is what the amount of ground cover looked like on this site, but you always want to verify that before you go reporting it. So to review, our information provided by data gathering activities needs to be both accurate and credible. Data management presents many potential sources of non-sampling errors, and these affect accuracy, and they are not detectable statistically. We need to anticipate potential errors and take steps to avoid them. And we can use best management practices to reduce and eliminate these avoidable errors.